Hello. So I'll do representation theory today. We'll get into the real thing and in a compact case. So goodbye finite groups. We'll go to compact groups and try to do everything for them. Representation theory, Peter-Weyl, Tanaka duality, also easiness. A lot of things to be done today. Let's find this presentation. So here we go. Representations of compact groups. So very classical topics. All these things go back basically to Hermann Weyl and a few others like Brouwer, Tanaka. So have a look at all this. So look at the closed subgroups of UN. Okay, not all the compact groups, but the so-called compact Lie groups, the closed subgroups of UN. That's important. Simplifies many things and covers all the interesting examples. So co-representations, the continuous morphism into unitary groups. So the basic example, the embedding itself into UN is a representation called the fundamental and will be denoted by pi. As a technical comment now, let's assume that these representations are smooth, but in the sense that their coefficients are polynomials in the coefficients of pi. I mean, in the GIJ, the matrix coefficients. Why I call this smoothness? Because there are some results stating that in this case here, where J is a closed subgroup of UN, it's actually a Lie group, so it has a C-infinity structure, and it's exactly the smooth representations. But technically, so we don't want to get into that thing, which is a bit complicated. So we'll just make this definition. Smooth for us will mean this thing here. Coefficients are polynomials of the GIJ. We'll use this later, proving Peter-Weyl. Now, what can we do? Representations. We can make sums. I mean, you just put them like this on the diagonal. Okay, to put two unitaries on the diagonal, it's unitary, of course. We can make tensor products. That's also a unitary. Tensor unitary is unitary, right? We can also take conjugates. So if you put bars everywhere on your unitary, it remains a unitary. Now these things, so remember, we have only one example of representation which comes for free. It's the fundamental one, right? So, but with it, well, we can take its conjugate and then take tensor products between pi and pi bar. And this will be called Peter-Weyl representations, and I will denote it by P tensor K. But K, you see, I have to take into account if it's pi or pi bar. So that's why K will be a Kähler integer. For instance, pi to this guy here is by definition pi, tensor pi bar, tensor bar, tensor pi, tensor, etc. So Y stands for nothing, and bar stands for a black, stands for conjugation. Now, what else can we do? Yeah, we have a lot of definitions. The theorems will come, no worry. So we can talk about intertwiners between representations. So these are just rectangular matrices. I mean, they don't have necessarily the same size, the representations that we take, rho and mu. These are rectangular matrices which intertwine the representations in this sense. Now, if I take the trivial representation, I mean, just one by one matrix, things which intertwine one and rho are the fixed points of rho. These are denoted by a fixed rho. Also, if I take a rho equals to mu, these are the so-called endomorphisms of rho. I mean, these are square matrices now which commute with action. Also, I call equivalence to representations when the home space contains an invertible element. And finally, rho is co-irreducible when there's no intertwiners. Okay, so all these are definitions. And finally, one more definition. So I'm actually interested in this Peter-Weyl representation. So let's go back here. So you see, I can take pi bar, and tensor them. So these are the representations which come with the group. All the rest is a bit abstract. So I'm interested in computing somehow this home spaces between pi k and pi l. So these are things. I mean, these are linear spaces. Let's call them CKL, indexed by pairs of colored integers. And this is called the Tanakian category of G. So we'll get to that later, but basically that's the main point in representation theory, to compute this Tanakian category. Now, Peter-Weyl 1/7, so 7 slides here. It's going to be hard. So let's have it started. So Peter and Weil, that's things which happened before the war. They developed a theory which has many theorems, and there are actually four main ones concerning these representations. So in these 7 slides, we'll have the 4 theorems and also a few more technical things that are needed. So the first one is that any representation decomposes into the sum of irreducibles. This is something quite elementary because if you take the intertwiner algebra, so it's an algebra now, I mean, product of intertwiners and intertwiner. So it's a subalgebra of the matrices, and this is not very complicated. It's well known that it's a direct sum of matrix algebras. How to prove this? You decompose the unit as sum of minimal projections, and then each of these projections will determine a matrix block. Okay, so I use this thing here, which is not very complicated. Now, as you have this, of course, you just use the same thing. I mean, 1 is Q1 plus QK. You can define the subrepresentations by restricting the row to the images of these projections, which are invariant. And they are irreducible because if you want the intertwiners correspond to these full matrix blocks. So this is quite elementary. Basically, it comes from this, okay? Right-hand row, a sum of matrix algebras, and you have your decomposition. Now, second Peter-Weil theorem, which is also elementary, but well, you have to work a bit, is that any irreducible representation appears inside a certain Peter-Weil representation. So that's very important because if you combine it with previous result, let's go back here. So yeah, completely irreducible. This means that in order to compute all the representations, we just have to split these Peter-Weil things, getting this way all the irreducibles, and then you can sum if you want these irreducibles and get all of them. So very important. You see Peter-Weil plus 1 plus Peter-Weil 2 tells you that, yeah, that's the end of the game to decompose these Peter-Weil representations. So how does the proof goes? I'm using here the smoothness assumption. I mean, the coefficients, I was telling you about this in the beginning. The coefficients of a representation are by definition smooth inside the coefficients of pi, the algebra generated by the polynomials. Now, C pi, if you want, is a sum, not a direct sum. It's a sum of coefficients of pi to the k, right? Because pi to the k are just tensor products between pi bars. We get all the polynomials in the uij's and uij bars. We get everything. So now if you work out a bit, I'm using all the time you see these coefficient spaces. And if you work out a bit the correspondence between representations of the coefficient spaces, that has all the good functorial properties. I mean, subrepresentations are mapped to subspaces and everything. So from this, you see, so 0 has to live here. So it's the coefficients of some big sum of Peter-Weil guys. But now I can apply Peter-Weil 1 and I'm done. Okay. So very nice. Now, what else to be done now? In order to get more advanced things, we have to integrate over our group. So for Peter-Weil 3 and Peter-Weil 4, we need integration. So let's take a bit of a break now and integrate over our group. So of course, when the group is finite, there's no need, you have the integration there. But when it is continuous, you have to prove that the uniform integration exists. Okay, so in 3 slides now, we'll prove that the integration exists. If you're interested only in finite groups, just ignore this. I'll be quick anyway. So no need to click too fast forward. Yeah, that's the claim. So any subgroup has a hard measure which is unique. Hard means invariant to the left and to the right. If I take E, a part of the group, measurable, can translate to the left, to the right by G, again the same thing. And the construction is as follows. You take any probability measure on U, and then you convolve it. And the idea is that the more you convolve it with itself, the more it's going to be invariant. But you cannot really take a limit there because it won't converge. You have to take a César limit. Okay, so the César limit, the convolutions gives you the hard measure. And in addition, there is one more thing which is important, which makes the relational representations, is that if you integrate the coefficients of a representation, you get exactly the projection onto the fixed point space of the representation. Okay, so there are 3 things here. There exists, it's given by this, and by this. The idea of the proof now will be to take this and show that this guy satisfies this. And this will give us everything. So we have to construct these zero limits starting with a probability measure. And the first thing is, let's start just with the positive mass one measure. Not necessarily positive. I mean, there might be some chunks there of the group G where the measure is 0. Okay. So my claim here is that if I take the zero limits, I'm actually interested in integration, not in the measure. So let's formulate everything in terms of integral. So I'm taking this zero limit as before, and I integrate a function with respect to it. Let's call this integral over g, but somehow depending on u. Okay, I use this abstract symbol for this functional, if you want here. Then the first claim is that the limit exists. And then for any representation, if you integrate the coefficients with respect to this guy here, you get, well, not exactly the projection onto fixed B, because remember, nu is not yet faithful. So that's going to depend on u. And it's actually the projection to the one eigenspace of this matrix here, then by integrating with respect to nu the coefficients. So that's a bit of a technical thing. And actually, it's just standard linear algebra. Everything happens on the coefficient space 0. Why? Because first of all, the existence, it's enough to prove it that the integral converges for any coefficients of a Peter-Weyl representation, right? Anything is a linear combination of Peter-Weyl representation coefficients. So this thing here is actually, it's enough to prove it for the Peter-Weyl representation. So it's a particular case of this thing here, draw being one of the Peter-Weyl things. So it's enough to prove the second part. And the second part, to just use the fact that the zero limit actually of a matrix, which is, well, of norm less than 1, is the projection to one eigenspace of the matrix. So it's really standard linear algebra. It's just linear algebra in finite dimensions on the space, and that's the trick. Zero limit of a matrix is the projection to the one eigenspace. So that's our first thing. And with this, now I can conclude. So now let's assume that mu is really a probability measure. I mean, strictly positive. There's no part there on G, which goes to 0, has measured 0. So let's go back to the previous slide. What we must prove in order to finish and everything is just the projection to the one eigenspace of this guy here. Actually, is the projection to the fixed points. So we want to prove that this one eigenspace is the fixed points. One inclusion is clear, so you just have to prove that if it's a one eigenspace, then it's a fixed point. That's all. In the other sense, you just integrate with respect to nu and you get it. So you just have to prove that this implies this. And now, well, we use the standard trick in probability or operator algebras or whatever. If you integrate something which is positive and you get 0, then your positive thing is 0. That's the trick in probability or also in operator algebras. For those who know, A star is 0 implies A is 0. That's the trick. So we have to, so we put everything together here. We want to prove that this thing vanishes. Size a fixed vector means that these guys vanish. So just put them all together in a big thing. The sum of all the guys we're interested in times their conjugates. So if we're able to prove that this function is 0, we're done, okay? And how to prove that it's 0? Well, you just compute this thing and you get something like this, very simple. And now, if you integrate this with respect to nu, remember, we know something with respect to nu here. That's our data, okay? We want to obtain something universal, not depending on nu. So if we integrate with respect to nu, of course, you will get 0, right? It can only be 0. So you get this. But nu is now a probability measure if it's positive, so if it's 0, and we're done. Okay? So when it comes from this trick, it's a trick, so probability operator algebras, you name it. So yeah, A star is 0 implies 0, let's say. Okay, so now we have our measure. We can develop Peter-Weyl theory. So two more results. So first of all, the space of coefficients of pi, which is actually a dense subalgebra of the continuous functions, right, by Stone-Weierstrass. And it's also C-infinity of G, actually, if you know a bit more things, but we don't need that. Decomposed as a direct sum of matrix algebras as a linear space, of course, not as an algebra. The sum has been pairwise orthogonal with respect to integration. So is this true? Well, you must prove that, well, this is a stronger orthogonal than direct sum. So you have to prove this thing. To irreducibles, if they are not equivalent, the coefficients are orthogonal. So for this, with the integration, you take this projection here, this matrix here. So, but by what we said before, this is the projection to the fixed points of this tensor product. Now, if you do some algebra, this kind of Frobenius isomorphism, it's quite simple. It's the home, but things here were assumed to be non-equivalent, so it's zero actually, the space. So finally, that projection is zero. So I got it. The coefficient states are orthogonal. These guys are all zero. Very good. Now, final thing, Peter-Weyl force, so the characters, which are the traces as usual, belong to the algebra of smooth central function. By central, I mean f of j is f of ag, and form an orthogonal basis of it. So, well, the characters, of course, are central because traces B, trace BA. So the actual only tricky thing is the norm 1 assumption, because orthogonality, we know it from Peter-Weyl 3. And for norm 1, well, you integrate this, and once again, it's exactly as in the previous slide. We get some coefficients of some projection, which projects here onto 1. So it's 1 over n, we get 1. Okay, so everything finally, we're done with Peter-Weyl now, very good. Everything comes from here, yeah. Advanced Peter-Weyl stuff comes from this thing here, which is a construction of hard measure. Whenever we integrate coefficients, is the projection to a fixed point space. And actually, this is we'll study more of this in the next lecture of the integration. Weingarten formula, it's called. We'll do that later. It's always based on this idea. That's the formula of integration. Okay, so now Peter-Weyl. Now easiness, very good. Let's do something easy. And well, let's start with the difficult thing. It's going to be easier later. So the idea is that the closed groups of UN are in correspondence with the corresponding Tanakian categories. So in one sense, we know that's the Tanakian category. In the other sense, given well, I won't say here what's the list of actions for Tanakian categories, but you can imagine it's a category as a tensor operation, all that. So given such a category, how to construct a group? Well, it's just dumb. I mean, you take the unitary matrices, which are intertwined by all these guys here. So this must happen for all K or L or integer and anything C. So it can all be this, right? If you want to prove this, so you have to prove that two things are inverse to each other. In one sense, it's clear. In the other, you have to work a bit. It's quite technical. So this is due to Tanaka and Krein independently. Heavily uses Peter-Weyl. Now this is pretty good because we can talk about easiness. So what's the simplest situation is when our group appears from a simple category, from partitions. Now this notion of category of partitions, I mean, it's stable on all the operations. Partitions will be K points and L points. Stable on concatenation, vertical and horizontal, partition, everything. So now we can say that G is easy when this Tanakian category is spanned by partitions. The linear map associated with partitions is given by this formula here. These are Kronecker symbols, depending on whether this is fit or not. Let me show you right away some examples to see how it works. So this is a Brouwer's theorem. ON, UN are easy, and also the reflection groups H and K are easy. The categories being the pairings for ON, matching pairings for UN, meaning white has to connect to white or black to black, or the horizontal white to black. And here for the reflections, you get partition of even blocks and matching with even blocks. So this is Brouwer, also known as Shrew-Weyl, Tanaka, all this. So this is very interesting. Now we'll see next time applications on this. And now regarding other groups, the stochastic ones are also easy. You can prove that. SN is easy as well, coming from the all pairings. The reflection groups are all easy. Also SO2, SO3, SPN are some host pairs in some sense. However, things defined using the determinants are not easy. So that's how the situation. We'll see more of this application next time. So see you soon.